So I learned essentially to work on elliptic PDE through the thesis.
Mm-hmm.
And so since then, almost all of my work has involved partial differential equations. From geometry or in complex analysis, it's all involved partial differential equations.
So, but there are other problems in geometry you worked on, the Nirenberg problem.
Oh, there's something that's been called the Nirenberg problem. Right. This is to, again, look at a Riemannian metric on this two-dimensional sphere, and it has a Gauss curvature, and the question was, which functions can you prescribe on the sphere as Gauss curvature for some metric? So I posed that problem. I gave it to a student, and we solved. He couldn't solve it in general, but he solved the perturbation problem. You're perturbed from constant Gauss curvature.
Right.
What he did was generalized later by Moser to a case where the Gauss curvature, this function is symmetric. And then the general case turns out to be false. Counterexample was produced by Kasdan and Warner. They found a necessary condition on this function that you prescribe as curvature. And since then, there's been further work. People have produced sufficient conditions, and people are still working on it. Right now and then, I get a paper or somebody working on a so-called Nirenberg problem. Well, some activity. I did a paper on rigidity. And so there's an open problem, classical open problem. You have a closed surface. Can you deform it continuously isometrically? That's an open problem. It's been open for 150 years, this problem. A counterexample was produced a few years ago of a polyhedron with corners that could be deformed continuously. But a smooth surface, it's not known.
Mm-hmm.
People had proved a number of years ago that a convex surface is rigid. Cannot not only deform it, but if you have two convex surfaces which are isometric, they are really the same surface in three space. And so I extended that result to something like a tube, like a tire tube.
Mm-hmm. Mm-hmm.
So it has a some kind of tube connecting inside, and I extended that using partial differential equations, and I had an assumption that I needed, and I raised the question: do you need that assumption? And the assumption was, in this closed tube of negative curvature, can you have a closed curve which is asymptotic curve on the surface? And my theorem says assume you could only have one, but maybe you could have more. A few years ago, a Russian paper appeared showing that you could only have one, or none rather, but using analyticity. So it's still open in the general case whether you can do it. And then I mentioned this Alexandrov paper. What he did, he proved that if you have a hypersurface in Rn, which is embedded, closed, smooth hypersurface with constant mean curvature, then it's a sphere.
Right.
And for many years, people tried to get rid of the embedding hypothesis. And then an American mathematician, Wente, gave a counterexample of a two-dimensional torus in R3, which intersects itself and has constant mean curvature. So
I did not know that.
Yeah, and then Yan Li worked on an extension of Alexandrov's theorem, and then together we worked on a different extension, which was if you have a surface embedded in Rn, hypersurface, and if you choose some direction, say call it direction xn direction, and if the mean curvature for two different points on the surface, if one lies above the other, the mean curvature, the higher one, is bigger than or equal to the mean curvature below, then what we tried to prove is that in fact they are equal and the surface, hypersurface, is symmetric about some plane perpendicular to that direction. So we proved that. In fact, it's a rather recent paper, but with some hypothesis, and we conjecture that that hypothesis is not needed. So there's another open problem, which I hope somebody will solve.
I mean, I know you've always been fond of Alexandrov's original work.
Yes.
Told me that it's a paper full of ideas.
Yes, and he did other things. He was an excellent mathematician.